Number 69 will be the first one I start up here. The reason I chose these two to collect and to have you do on your own, part of this for the calculator entry, and I'm not going to bring up my graphing calculator on here because we've done it several times, but just for speed and for accuracy, these have some good calculator parts to them. And then the other one I chose, number 71, I like part C mathematically, but a lot of these, the reason I chose these two is for their calculator entry. This one does say you can use your calculator. So when you're given the two functions, what I would suggest you do is immediately go enter this one into y1. That's obviously this curve. I would go enter g of x and y2. This one's obviously your exponential graph. And so what you have on here is your y1 and your y2 intersecting to create the solid R, or the shaded region R. So the first question you're usually asked with these is to find the area of the region. And so what I'd like to do on this one is, when we're finding the area, we really need to know our limits of integration. So the first thing you should do on your calculator is go take a look at the graphs of y1 and y2 and go get a calc intersect on that. And if you need to zoom in or alter your window so that you can get a good view, go ahead. So once you find those intersections, and again, you go calc intersect that. I'm not going to do all the arithmetic involved in all the calculator entries, etc. I'm just going to do the general overview of these. What I highly suggest you do is whatever you get for your calc intersect here, I would take that whole entire decimal and I would store it in, say, A or B or C or something. Likewise, I would take wherever this intersection is here, write the whole decimal, and store it in B. That way you don't run the risk of entering it incorrectly. And that way when we get to the end and we round to 3 decimal places, we won't have rounded once and then twice and then again and then be off. So that's what I would do first, is just go take my calculator and get everything stored in there. The functions in y1 and y2, their intersections, the x value of the intersections in A and in B. All right, so remember when we're doing the area, we are going to integrate and sum up all these little rectangles that stretch across from intersection 1 over here at A to intersection 2 over at B. So we're going to integrate from A to B. Make sure if you're doing this on the AP test, you have to tell them what A is. So you have to say A equals B equals, but if you do that once, you are allowed then to just use those variables as your limits of integration. Likewise, if you're going to store these in y1 and y2 and then use them within your integral, you should define them at some point so that the graders know what y1 and y2 is. I would almost say you might even just want to write those functions down, but when you're doing them on your calculator, use y1 and y2. What I mean by that is my top function here, the red one, is 6 cosine 2x minus 1. I need to take that function and I need to subtract the lower one, which is the blue one, for e to the negative x minus x. And I need to integrate that all with respect to x. But when I go do it on my calculator and I go use Math 9, what would be easier is if you just brought up y1 and then y2 to save you the entry and from accidentally entering stuff wrong. Remember to do that, to bring those up onto your screen. You hit your vars option. So again, I'm not going to do all the calculator purposely. So, and you go over to y vars, you choose function, and then just press enter. So vars, y vars, function, and then choose whichever function you want. I think that's the easiest way to do that. And then you guys can go ahead and get the answer for that. I'm not putting the answers on here. Remember, you are either to round or to truncate, either one's legal, at 3 decimal places. All right, part B, finding the volume of the solid when I'm revolving around the x-axis. The x-axis tends to be the easiest one for us to revolve around. So if I go take a look at my picture and I'm revolving this way, Again, this will create washers. My formula for the washer is that I need to, again, don't forget the pi out front. It's pi r squared h for the area of all those cylinders. With a washer, I've got that hole in there, so I'm going to integrate again from A to B. I'm going to integrate r squared minus inner radius squared, and I'm going to do this with respect to x. So really, my only challenge here is to determine what the big radius is and what the little radius is. So back up to my picture, draw one representative rectangle. Remember, you're going to picture spinning that around, creating a disc. A washer. And so you're going to take all those washers and you are going to sum their volumes up, creating the volume of the solid. All right, so as we do that, we really just need to know what the big R and the little r is. And remember, big R is from the axis of rotation to the outer edge, which would just be the y value there, and that's the red function. So my big radius is really just 6 cosine 2x minus 1. I'm going to call that y1. So I've got pi times from A to B, my first function. Don't forget to square it. And then my inner radius on here, again, if I go up here, is from the axis to the inside of the curve, which is really just my blue function. So make sure, again, that you don't forget to square that in there. It's pi r squared h, and the height of those right here is represented by our dx. And I will have, you need to go finish that off on your calculator. Again, it's easiest to draw these up under your stored values. It's easiest when you math 9 it just to put these in using that vars option. So in the next one, the region R is the base of a solid. So again, I'm going to erase this up here. So now what I got here is back to region R. It's representing the base of a solid, and off that solid I'm going to pull out and make a three-dimensional figure. I'm going to sweep across perpendicular to the x-axis. Okay, so what I would suggest you do is what says perpendicular to the x-axis, immediately draw that down. And I'm going to do semicircles. So really what's going to happen is I'm going to have this is the diameter of my semicircle. I'm going to pop it up, and then I'll do another one and I'll pop it up, and I'm going to sweep those all the way across. And so let's go put that on there. And so really what this involves is finding the area of that semicircle, and then again I'm going to sum them up, meaning I'm going to integrate all the way from A to B again. And that will give me the volume of that solid. And again, you got to picture those semicircles popping up out of the screen. So my volume formula is to integrate the area, and I'm going to, with respect to x, because it says perpendicular to the x-axis, so I can still use my A to B that I have stored in there. And remember, for my semicircle, my area is 1/2 pi r squared. So your challenge is, let's go write that part in here. I'm going to integrate from A to B 1/2 pi r squared dx. Well, what is the radius is my question. Well, the whole diameter is the difference between the functions. So my whole diameter would be the top function, which would be y1, minus the bottom function, which would be y2. That's the whole diameter. However, I do need to make sure that I cut that diameter in half, and that will give me my radius. So be a little careful with that you really think that through, that the area of the circle requires the radius, the distance between the functions gives me my diameter. So that really when I go in here, I would do 1/2 pi, and my radius itself is 1/2 of y1 minus y2. And I'm going to have you guys go do the calculations on that. All right, so finish those up. The next one I want to go over is number 70. I like number 70 because they have you go around the y-axis a little bit, and I also like the last question. So the first one I don't know that you need a whole lot of help on, but this one does say no calculator. So when I'm finding the area, I'm not going to go through that one. You should easily be able to find the area with doing your top function, which is y equals 2, minus the bottom function, integrate from 0 to 8. But please do that by hand. It says no calculator, so I should see manual integration on that. There is no calculator on this problem. All right, the next one, it says to find the volume of the solid when we go around the y-axis. Now, This is why I like this one, because they usually have you go around the x. So when we're finding the volume of the solid, again, we go from the axis to the outer edge, and there would be no hole created because this whole solid is butted up against the y-axis. So I've got a disk problem going on here, but I'm doing it with respect to y. My differential is along the y-axis, so really what I've got going is my disk is kind of going like that. Alright, so on this one, what I would like to do here is still, don't forget the pi when you're doing your volume. And it, you can still think of it as big R squared minus little r squared, but the little radius is 0. So really what I need to integrate is just r squared, but with respect to y. So again, when I'm doing my limits of integration, I am going to be summing these up from the bottom to the top, and you got a picture whipping that disk around. It's going to create kind of like a funnel shape here, each one created by a disk. So when I do that, my integration would go from 0 to 2 on that one. So there you go. My only deal now is, well, what is the radius? Well, again, the radius on this one, we are going left to right. We're going along the x-axis, so I need to figure out how far this is. Well, again, back to the original function. The original function is x comma cubed root of x. And when we go with respect to the x-axis, we do want to know how high it gets. But when I go with respect to the y-axis, I need to solve that for x in terms of y. So if I go back up here and undo the cubing, I would have my x distance is really y cubed. All right? So kind of think of that. And sometimes it helps to think of a point. Sometimes it helps to think of, well, the point 8,2 is on the function. Cubed root of 8 is 2. But if I'm given the y value, I'd have to cube it to get the 8. So my y differential kind of determines that, and I know that out this far, along this, it's always going to be y cubed. So when I integrate that, I'm going to have pi, and again I'm going from 0 to 2 along the y-axis. I've got y cubed I need to square in terms of y, and then you would integrate that by hand. Leave your answer in terms of pi, obviously, because you don't have a calculator. All right, so this last one is the one I really wanted to get to. Unfortunately, I only have 12.5 minutes, so I might not be able to get the whole thing in. However, this is talking about a rate of change, and I like it because it ties in a whole bunch of different things. So the solid in part B is going to model the vase. So what I'd like to do is go get a picture of that vase. It's looking like this, and it's measured in inches. The vase fills with water, so I'm going to go put a little water in there, and it's filling at a rate. So that's giving you the derivative of the volume. So you should do dV dt equals 6. When the water level is 1 inch, how fast does the water level rise? So let's go put a little h on here for the height of the water level. And you're looking for dH dt when the height is equal to 1. So I've got to take that volume, its rate of change, to help me find the rate of change of the height. Well, as with all of our related rates problem, we need a formula for the volume. Well, we did it in part B, and we did it was pretty straightforward. However, that was for if it was too high, and I have an unknown height here, and I'm changing over time, so that volume is changing, the height is changing. So really what that means is the top of the integration is the height, and as I fill it up, that's an unknown. I'm going to stop that height at 1 and see what's happening, but it is varying as the clock starts. So we've got our volume is equal to pi times from 0 to h y cubed squared, y to the 6th, dy. All right? And there's a long way and a short way to do this. I'm going to take you on the long way and then talk to you about a shortcut, but I actually don't even have time, so I'm going to let you work that out. And once you get your volume cleaned up, so you're going to integrate, get volume, then you're going to do dV dt. Remember, you're going to have a little chain rule action going on because you're going to be putting the height in, so you're going to have to be multiplying by dHdt when you're done. All right, so I'm not going to finish that one off, but this is a good start for this one. Keep in mind, get it down to a formula involving dHdt and h, and plug in a 1 for h and plug in a 6 for your change in volume. And if you do that correctly, I'm going to let you show the work, you should get, I'm going to give you the answer to this one, 6 over pi Related rates always require a label, so that'd be inches per minute. And I want